Hi guys, welcome back to 100 Days Machine Learning Crash Course. In this session we are going to talk about linear regression, linear models for regression. Okay, so the goal of regression is to predict the value for one or more continuous target values given an input vector x. So we have an input vector x which is d-dimensional, and then we want to predict a target value t which is a continuous variable based on this input variable. And actually we already have seen an example from this, which was polynomial fitting. And this is actually a certain kind of linear models for regression. Linear models are actually a broader class of fitting models rather than just polynomial fitting. The simplest form of linear models is to just combine the linear combination of input variables with the weights. So the y in this case would be w0 plus w1 x1 w2 x2 wd xd. Okay, so this is a linear combination of input variables and the linear combination of the weights. Okay, sometimes as we saw in polynomial fitting, we create this function to be non-linear with respect to the input variables, but linear with respect to model variables, which are w's. So in this case we have a set of fixed nonlinear functions which we applied them to the input vectors, and then run this linear combination of input variables to get the output. We call this function basis function. So it is important to know that even though these are nonlinear functions when we use them in linear models, but they are nonlinear based with respect to input variables, but they are linear with respect to model parameters. So as we have seen for polynomial regression, in 1D case we had something like this. In this case, as you could see, the basis function in this case is polynomial, and this is actually a nonlinear function of the input variables x, because it has x squared, x cubed, and x to m minus 1, which is a nonlinear function of x, but it is a linear function of model parameters because the model parameters are just the w's, and this is a linear combination of w's. So although our basis function is a nonlinear function of input variables, but it is a linear function of model parameters. In probabilistic view, we are going to find the probability of target given the input vector x. We saw that if we set the loss function as least square, the optimal solution of this example is the expected value of the probability of t given x. So it means that this is a conditional average of target values. So in linear regression, we just have linear combination of the weights and w's. So we have w null, w1 x1 to wd xt, and just note that our input feature has d dimensions, so it is something like x1 xt transpose, and so this is the linear combination of these would be something like this, and this is the output variable. And when we use the basis function phi j of x, we could write the linear combination as w null plus w1 phi x1 to wm minus 1 v of, actually this is v1, vm minus 1 x. So in other words, if we actually add a dummy variable, that dummy variable by null of x, we define that such that it is 1, so we could write this is as follows: the y of x and w will be the sum over j wj phi j x, and we could write this in vector form of w transpose phi of x, in which the w are the model parameters, and it is a vector of w1, actually w0, w1 to wm minus 1 transpose, and the phi is phi 0 to phi m y minus 1 transpose. So we could actually select different possible nonlinear kernels for changing the input variables, but still we have linear models for obtaining parameter models. So maybe it is better to introduce some common basis functions that commonly used in real-world applications. One of them is actually we see that it is the polynomial kernel function. That is something like this. It is defined as x to power j, but this is a drawback. This has actually a major drawback, that they are global function of the input variables. So if they change a region, they actually affect on all other ranges. So if we add this term in some place to change the function to be something like this term actually affect all of these regions also. So it maybe affect all of the region outside this region, something like this maybe, and it is maybe something that undesired for us. So we have other kernels also that we could work with. One of them is Gaussian basis, which is very famous one, and it is defined as minus x minus mu of j squared over 2s squared, and the s is actually a parameter that you could change. It is the spatial scale, and in this case, as you know, the shape of this basis function is something like this. So in this case, if you change a region, as you could see, it has nothing to do with this region. So you could change just one region without changing and affecting other regions. This is very good feature of Gaussian basis functions. So now we are going to see real world application and real world example of linear regression. Okay, now we want to see an example of how to use scalearn to do linear regression. So the example is from the data set of the scalearn itself. It is the diabetes example, in which you have some features and then you have some target variables, continuous target variables, that we want to use a linear regression model to estimate a linear model that passes through all of the points or is very close to those points. Okay, it is better to explain it line by line to for you to getting familiar with how to use Python in order to use that in data science approaches or machine learning applications. So our main purpose is first we should, so our main purpose is we want to create a linear regression model for a data set. So first we should load our data set. Because the scalearn has this data set, we should just import the data sets from scalearn and load them in diabetes. If we print diabetes, we have as you could see, we have data and the target values, and the data are our features and the target values are our regression values. So as you could see, in here we just use only one feature. Maybe it is not a very good idea to just throw away all of the other features, but in here, for sake of simplicity and because it is just an example, we just used one feature from the diabetes dataset. Then after that, we want to train our model, and we want to have the test phase. So we should split the training and testing data. For this, we just separate all of the data and exclude just 20 data for test. And so if you this means that from 0 to the end minus 20, so maybe it is better to write it there. If we have our data is something in a list, it is something like this, and this is x of minus 2 means from 0 to the end minus 2, so it is from 0 to there. And as you could see, we split them for training, and for testing we just used the remaining ones. So it is from minus 20, which is from, if it is minus 2, it is from there to the end. In general, when you use the minus sign in the indexing, means that it is from end. So if you have something like this, the x0 in Python means that you want to select this element. The first element of the list is x0. But what if you want to select the last element? The last element is x minus 1 in Python, and this is x minus 2, and so on. But from this way you have x0, x1, and so on. So this is the minus indexing. So in here, as you could see, we use the last 20 data for test our regression model, and we also separate the same number of targets for training and testing, because these are the features and these are the corresponding target values. So after that, we just created a linear regression model, and the good news about it is that the sklearn itself has a linear regression model. So from sklearn you could import a linear model, and then you just create a linear regression model for that. After that, this is actually create a linear regression object from you. Then you want to fit your model on your training data. What does the fit mean? It means that when you created your model, means that you have some parameters for that, but the parameters are not known yet. So if you want to train your model, means that you want to derive these values. So when you use the fit method of regression object, it is actually uses the training data set. This is the training features, and the second argument is training targets, and then with this line it finds some weights for the linear regression model. After that, we want to test our model. For testing our model, we just pass the diabetes test data to our model, and if you want to use your model to get some new values on on a new data, on a new test data, you can use the predict method of your model. So we use the predict of our regression model on test data and got the prediction of our model. Then we just printed the regression coefficients, which are the values of W null, W1, and these weights, and also we print the mean squared error on the test data. After that, we just with Matplotlib, for visualizing the data, as you know, you should import matplotlib.pyplot. Then we use that to show the test data and also the prediction of the network. So let me to run that. Okay, as you could see in here, these are the actual test data, and this is our linear model that predicts the test data target values. So as you could see, it is a linear model, and in this case we got this mean squared error. Okay, maybe you want to use polynomial basis function to increase the accuracy or increase the mean squared error, or decrease the mean squared error. So in this case, we actually could extract some polynomial features from the input variables and then apply linear regression model on that. So let me show you from this. So first we could apply our basis function to the input variables, and then apply a linear regression model for the input data. For doing this, you could just use the scalearn as follows. So for doing this, as I mentioned, we just need to apply the nonlinear basis function to the input features. So for this, the scikit image itself has something called polynomial features. As you could see in here, we could apply polynomial features on our data. Then with poly.fit transform, we can get the transformed features, then apply linear regression, our linear regression model on this new transform data. So as you could see in here, you could set the polynomial degree as what you want. Then it could be like 2. Then you transform your data. So the output of this would be this. As you could see in here, we have now our data was one-dimensional. Each of our entry data was one-dimensional. Now we applied our basis function on that, and we set the degree to, so this would convert to we call this x, so it will be convert to x to power 0, power 1, and x squared. Okay, so we could actually print the num of the integers, as we could see in here, is 422, and in here we have 422, and each of them has 3 features. So each data that has just one entry converted to 3 different feature with our kernel nonlinear kernel basis function, because we set the polynomial order of that too. Now we could apply the linear regression model to the transform data. As you could see in here, we just use the same linear regression model and apply that on transformed data trained with the same targets. Then we could get the prediction on the test data with the same polynomial we transform, because we should apply the same polynomial feature extraction on the test data. Then we could get the prediction. That's so simple. So first we should apply our basis function on the input data, then train our linear regression model. Okay, let's get back to just the theory things. Now we want to talk a little about maximum likelihood and its relation with least square. If we suppose that we have a data set that has x1 to x and samples, and they are IID, means that they are independent and identically distributed, and then let's assume that the probability of target given the data set and the weight of the model and the variance of the Gaussian distribution is actually in here we suppose that we have Gaussian distribution on our samples, so we could write the maximum likelihood as the product of some Gaussian distribution with the mean of W transpose phi xn and beta minus 1, which determine the variance of the model. So it means that actually it says that if we have one training sample in here, it comes from a Gaussian distribution. If this is just Tn, it comes from a Gaussian distribution which its mean is a linear function of W's. It is its mean and it has some variance. So it could be something like this in here, maybe. In other words, around T of n, and T of n, the mean of T of n is W transpose phi xn. We have a Gaussian distribution for this data point. So it could be something like this. It could be here, here, here with some probability. Okay, it could be around the mean point, and the average point is W transpose phi xn. Then if we use if we take the log to create the log likelihood, because this is the likelihood, so if we take the ln probability of t given x, w, and beta is equal to n over 2 ln of beta minus n over 2 ln 2 times p minus beta e subscript d of w, where the e is 1 over 2 sum over target values minus W transpose phi of x and squared. So as you could see here, this is squared loss. This is actually squared error. So it is very interesting result if we apply a maximum likelihood on the model that the data comes from a Gaussian distribution with the mean of W transpose phi of x. It is equal to the to the fact that we have cost function of least square error. So if we minimize this error, which is the least square error, it means that we are maximizing the log likelihood of the model that its samples comes from Gaussian distribution. And we are going to talk about this fact maybe later in deep learning, and specifically in super resolution network. We will see that this error produce some problems and blurry effects in there, because it just relies on the mean of the Gaussian distribution. Okay, anyway, the good news for this cost function is that we could minimize that analytically. So if you minimize that with some just linear algebra manipulations, you will end up with these weights. These are the optimal weight vector. So you could actually, instead of using scalar package, you could yourself put your data in a matrix of transformed with the kernel basis, and m minus 1 x1 phi of m minus 1 xn. Then when you put your data in this matrix, you will just need to plug that phi into this equation to get your optimized W, which are the weights of your model. Okay, and the T is your target value. So it is very good that we have analytical solution for linear models. Okay, so as you would probably remember, we talked about regularization. We needed regularization in a case that when we have low number of data, the model is prone to be overfitted on the training data. So to prevent overfitting, we need regularization. Okay. So regularization for preventing overfitting. And as you remember in our example, we include an additional term. So if this is the square error, we added another term just based on the W's, which we call that regularization. And it could be, for example, we talked about that, it could be the second norm of the weights. This is actually means that W1 squared 2 and Wm minus 1 squared. Okay, so this is actually the second norm of the weights, because the weight is a vector, so the second norm of that is this one. Okay, the second norm actually is squared. Okay, and we call this in machine learning terminology, we call this weight decay term. Why? Because we will see in neural network part that this term tries to close the weights to 0. It is obvious from this equation that this term does not want to let the W to be big, because if the W's become large, this term increases, and then so our total error increase. So this term try to reduce the amount of W's and closes them to 0. So we called them weight decay, and if you heard that in deep learning, it is very commonly used in deep learning for regularizing the network. And again, if we solve this problem to obtain some W that minimizes this equation, we have analytical solution for this problem, and that is lambda I, which I is the identity matrix, phi transpose phi invert, and phi transpose and our target. So as we could see, we also, in this case, we also have analytical solution, which is great. We will typically call this ridge regression. Ridge regression means that the linear regression itself plus regularization term, we call that ridge regression. Okay, so, and sometimes instead of using this, we will use the norm, the first norm, which is just this. In this case, we will call that lasso, and we will prove that if lambda is large enough, then some of our coefficients of W would be 0, and it means that we have a sparse model. So in when we are going to find some sparse models, we will be using the one norm as the regularization of our model. So if you want to use ridge regression with scale learn, you could just search ridge regression scale learn. Then you could see that in here it says that okay, it is just the least square term plus, instead of lambda it uses alpha, so it is not any difference. And this is just the second norm which we talked about. That the second norm, sometimes called for the regularization, we call that sometimes L2 norm. So it is L2 norm, and we call the one norm L1 norm. So as you probably know, and you could see that it has also an example. So you just need to import the ridge regression from here, and then just created some random samples. Then you just pass the alpha, which is your regularization parameter. So the most important part of having a linear regression model with regularization is the tuning of your regularization parameter. So as we already talked about it, we called it hyperparameter. So we could tune that with k-fold cross validation. So we could try different values for alpha, and then get the score on the validation dataset, and set the alpha to have the best value of validation score. And then you can fit your model, and that's it. You have your model. Then if you want to get the prediction on the new data, you could just use CLF or your classifier model, which in here it is not actually classifier, it is a regressor. So you could just use CLF.predict to get the prediction on the new values of your input data. So in this session, I hope you got familiar with in general linear regression models and ridge regression. These are very basic and commonly used methods for regression in machine learning. You could try them on different data set. For example, if you want to predict stock market price or stock market value or house price or these kind of data set that you have continuous target values, you could use these methods. And there are some public available data set that you could try these models to get you hands-on these methods and get to be able to examine yourself with working with Python and Scalar and these things. Also, maybe for getting better and be more professional in working with data sets, we are probably going to introduce pandas to work with different data sets, to visualize them and these kind of things in next sessions. But for now, you could just use public available data set in both the Scalar itself or in Kaggle competitions. There are some research competitions which you could use their data set to just examine yourself for deploying these methods. Okay, I hope that you enjoy from this session and hope to see you in the next session. Bye.